Hi all. So in the night, you might look up at the sky and you will see stuff there, like stars, maybe some galaxy, maybe the moon. But there's a lot of black in between. And this is not just empty, so there's not just nothing. You might think it's just black, but actually there might be black holes in there. And the question now is like, how can we actually observe something which is black, which we cannot see? And the answer to this is gravitational waves. So if we somewhere in the universe have two black holes and they attract each other because of the gravitational force, then what happens is they're spiraling inwards around each other and until they merge into one big black hole. And in the process, they send out gravitational waves. So here they merge, and you can see that kind of the ripple goes out. It's a ripple in space-time, which goes through a whole universe and at one point also arrives on Earth. And this is how we can actually observe black holes. So gravitational waves, as I said before, arrive when two black holes merge, and this system is described by 15 physics parameters, mainly like the masses of the two black holes. That's super interesting for physicists, also how far the merger happened from Earth and other physics parameters. Then this gravitational wave gets emitted in the process, it propagates through the universe and arrives on Earth. And we can measure this actually in our detectors. And Einstein never thought that this would be possible because it's a tiny, tiny deviation of the space-time. And the signal that we measure in one of our 3 detectors, 2 in the US, 1 in Italy, actually can look something like this. So here the gray lines is actually noise on top of the simulated signal, which you can see in like a color. And you can see that kind of you have basically an in-spiral phase where these two black holes move around each other. You can see the excitations getting larger and larger until the point where they merge into one big black hole. And this is the type of data that we're then interested in. But of course, we measure this, and we mainly want to know what is the underlying physics. So we want to know what were the masses which created this signal. And this is done by using posterior estimation. So we're interested in the whole posterior distribution over these parameters. So in our case, we're of course doing Bayesian inference. We don't want just to have a point estimate, but we want the full distribution because it could be a broad mass range which created the same signal. And this, of course, the Bayesian posterior gives us uncertainties, but also correlations between parameters, because, for example, the sky position, so the longitude and latitude of where from, like on our sky, the signal came from, of course, this is correlated. So why do we need machine learning to now solve this inverse problem? And the reason is that in gravitational wave science, the detectors are getting better and better. So we have a larger number of events. Here you can see like the curves over observing runs of like the cumulative number of observed signals. And currently we are here at the end of O4A, and we have like around, basically observe maybe around 5 events per week. But in the future, with future detectors, this will be around 200 events per day. And the challenge here is that standard methods to do this parameter estimation, so to get the posterior distributions, they need around minutes to hours or even days or weeks for a very complicated simulator for a single event. So if we have to do 200 per day, like we would need so much compute that we cannot solve this problem in the future. So the idea, of course, here is to use machine learning to speed this up and therefore like make new physics discoveries possible. And for this, we use the framework of neural posterior estimation. This is a simulation-based inference technique. And what you use is that you have a very good simulator of the physics which happens. In our case, that's given by Einstein's equation of general relativity. So what we do is we define a physics prior here. We sample from this prior, and then we use these samples to plug it into our simulator, and then we get simulated data out of this. And this could, like a signal here in frequency domain, could look like that. So we basically get samples from the likelihood, and then we use these pairs of prior samples, so parameter samples and data points, to train a density estimator, for example, a conditional normalizing flow or flow matching or diffusion model, which actually then gives us posterior samples, and we get this posterior distribution out of this. And once we have trained this density estimator on a lot of realistic simulations, we can then plug in an observed data point. So we can just, instead of using a simulation where we of course know the underlying physics parameters like the masses, we can now plug in a signal which was actually observed. And with this, we get then the posterior distribution based on our trained density estimator. If we now take this framework and apply it to gravitational waves, we of course have to have a gravitational wave simulator. And here now, previously I showed you the signal in time domain. So it's like a time series, but we can do a Fourier transform. So here you can see the simulated signal in frequency domain. And then we, of course, have to make it more realistic because the signal doesn't include noise. So we take measured noise from the detector and sample from this. So we assume in each frequency bin we have a Gaussian, and this noise curve here on the right gives us basically the standard deviation of this Gaussian. So how much noise we have in each frequency bin. We sample random realizations of this and then add it on top of our simulated signal. And this is something very realistic, which we would actually see in the detector. And this is what we actually then input into our density estimator and what we train it with. So to train the model, we do not only provide the data, but also noise, which happened right before this signal was observed into our network. And the reason is that this noise curve can shift over time. So when you start a detector, it takes maybe like you run it for 3 months, 6 months, then the noise can change over time. So you want to like let the model know how the noise curve has looked like right before the signal you want to analyze to give it some context information. And when we, for example, here in this case, use a conditional normalizing flow. So you feed in here the data D and the noise curve S in this case into an embedding network. And why do we need this embedding network? And the reason is that the data is very high dimensional. So I'm talking about 10,000 data points, 100,000 data points. If you have very long signals, you might have multiple millions of data points, and you cannot feed this, like use it as a condition for a density estimator. So what you want to do first is you're going to compress the data. We do this to compress it into like 100 dimensional representation, and then use this to condition a normalizing flow, which gives you samples from the posterior distribution. And this is a framework we call DINGO. And this network is then trained with negative log likelihood loss. Great. The challenge with what we have done so far with DINGO, or what Max Stacks and others have done so far, is that it doesn't really fit the real data, because real data is messy, as those of you who work with the real data probably know. And the challenge is that these data settings that are used within the collaboration to analyze these events, they vary. So for example, the detectors can be offline. So if we have 3 detectors, it can be the case that there's a noise artifact in one of them, you cannot use the signal, or that one of the detectors is offline for maintenance, or other cases. And then, of course, your input dimension of the data changes. It can also be the case that the frequency range changes. So here are different events, and you can see the number on the left. And you can see that the range here, so which frequency range is used to analyze the signal, also changes. And the reason why this might change is because there's a noise artifact, for example, at low frequencies, then you would cut this out and not use it to analyze it. And if you would have one fixed model with a fixed input dimension, we cannot analyze the data. So we need to be flexible, and we want to avoid having to train multiple very expensive models. So this is like the idea for the kind of the motivation for my work, which is to like take this DINGO architecture and just do one small thing, which is to replace the embedding network with a transformer encoder, because this gives us flexible sequence length as the input dimension. So we train now so we not only change the architecture, but of course we also have to change how the signal looks at training time. So we randomly basically remove tokens during training. And then we can, at inference time, since we've trained with a flexible setup, we can then change at inference time our settings as we want, as far as it's within the training distribution. And this is what we call now DINGO T1, so first version of a transformer. There will be more. And so to give you a quick idea of the architecture, we basically take the frequency domain data, we segment it into, put it into small segments, and then we use a tokenizer, which is applied across the whole frequency range and also across detectors. And because it's like a shared network, we have to condition it on which detector the data is coming from. So we don't use like a positional encoding. Then, of course, we have a token mask, because we want to mask some tokens. And then we have from multiple detectors the tokens, and we just stack them together, combine them with a summary token, and feed it into the transformer encoder. And of course, you all know what the architecture look like, but the physicists usually don't. So yeah, and in the end, we use the summary token, we compress it down again to around 100 dimensions, and feed it into the normalizing flow. And we train the whole architecture end to end. Of course, you could train, you could do some pre-training and then use some fine-tuning for the parameter estimation task. But in our case, we actually have a supervised problem, because we have labels, we have the parameters and the corresponding signal, because we generated it with our simulator. So why should we train an unsupervised way first and basically throw away the labels to then later do fine-tuning and include the labels in addition? And this actually works really well. And I will just show you one result because it's a very short talk. So what we can now do with such a flexible model. One interesting thing is, as I said, you can change the detector combination with which you analyze the same signal. So here we use the same event, the same signal, but we just mask out different tokens. So in this case, different detectors. And this has a lot of effect on the posterior distribution. So to give you some idea, here is like, this is the chirp mass, so it's a derivative of the masses of the two black holes. And this is very, it's very constrained. It's very similar for all three detector combinations, but you can see if you use more detectors that it gets more constrained, which of course makes sense. You have more information from about the same data from different detectors. Then what other interesting thing is like the sky position, so where the signal came from. And if you have a single detector, it could come from any direction. If you have two detectors, you can constrain it to like this donut shape, which geometrically makes sense. And you need three detectors to actually triangulate the exact position where this comes from. And you can see that it gets constrained very nicely with three detectors. For example, also the arrival time is like very peaked if you actually include the data from all three detectors. Great, so I just want to end here and let you have any questions. But first, the flexibility is now really great because we can quickly analyze a lot of events. So this is really cool because as I said, analyzing a single event with standard methods might take hours or days. And we can just basically, I can run on my cluster 50 events. And if I have enough compute resources, this might finish in an hour or something. Which is really great. I can also quickly change the settings, which is very interesting for physicists because maybe there's a noise artifact in one range and you want to see how this actually affects the posterior distribution. So you can basically take the same signal, just mask out different token combinations and see how the posterior changes. And in the paper, there are more examples of cool things you can do with it, including some cool physics tests. So basically, all analysis that I did in this paper kind of allows us to just train one model instead of 94 separate models, which we would have needed to train if we would have like a fixed input dimension. And if you want to just run this yourself, the model is online on Zenodo. You can just download it and then run inference with it. So there's a Colab notebook online, so you can like recreate this plot that I showed here if you're interested. Okay, great. Do you have any questions?